So, good afternoon, good evening, good day, wherever you are. Thank you for taking the time to join us in this GCEA webinar, the first in a series focusing on medical imaging technologies. My name is Mladen Paluta, and I have the pleasure of serving as moderator, assisted by Calibration Stavrianu, who is the very capable pilot for this 1-hour flight to better understanding of medical ultrasound imaging from both theoretical and operational perspectives. We have two excellent speakers lined up for you. However, before I introduce the first speaker, I'm going to invite you to participate in a poll. You will be asked to respond to a set of questions. Your responses will be captured and kept until the end, when the same questions will be posed. Your responses will once again be captured and compared to the first set. There are no prizes for correct answers other than the personal satisfaction of having benefited from the insights provided by our speakers. Please remember to make use of the chat to post comments. There is also a Q&A window should you wish to pose a question to either speaker. Some questions will be answered in the Q&A window, while others will be answered here in open session. So if we may commence the poll, here are the questions. We won't dwell for too long on these in the interests of time. So, first question, medical ultrasound makes use of frequencies in which range? From 20 kilohertz to 1 megahertz, 1 to 2 megahertz, or 2 to 30 megahertz. So please register your choice. I will move on. The basic principle of medical ultrasound imaging is similar to that of radar. True or false? Third question. Ultrasound waves are disrupted by air or gas. True or false? Kaliroy, if we could move on.
Please scroll down.
Fourth question, medical ultrasound systems allow imaging of blood flow in real time. True or false? And then last but not least, medical ultrasound systems are not able to produce 3D images. True or false? Okay, so I'm sure that many of you sailed through those. And as I said, we'll come back to the same questions at the end of the webinar. So I have the pleasure now of introducing our first speaker. Oh, there are the answers. So for question 1, we see that the choice is the third choice. For question 2, the majority of you felt that the principle of ultrasound imaging is similar to that of radar. For question 3, ultrasound waves are disrupted by air or gas, according to the majority of participants. Medical ultrasound systems do allow for imaging of blood flow in real time. And last but not least, medical ultrasound images are able to produce 3D images. Well, I can see that we've got a most informed audience tonight. In fact, if I'm not mistaken, you got all correct. So congratulations to you all. And now I have the pleasure of introducing our first speaker. Professor Aristakis holds a diploma in electrical and computer engineering, as well as an MSc diploma and a PhD in biomedical engineering. He has been a member of the Institute of Biomedical Technology, or INBIT, in Patras, Greece since 2008, and is currently the CEO and head of the Medical Technology Management Unit. He has collaborated with WHO in a series of medical device-related projects, has supervised the creation of medical device inventories for health facilities across Greece, and has played a key role in the design, upgrade, installation, and support of InBit's medical devices management system. Professor Attenuation has many research interests in medical imaging processing, reconstruction, and diagnosis, and related areas. He has also been a patent holder for a novel X-ray imaging technique. Aris, the floor is yours.
Thank you very much. Let me start sharing my screen in order to share the presentation. So, you can see my screen? Yes. So, thank you for the honor of having me here in order to make this presentation for the basic principles of ultrasound. We have a lot to cover, so I have to apologize from now if I bother you. So we start right away. Let's see a bit of the history of the ultrasound. First of all, discovery of the ultrasound in general as ultrasounds was done by Lazzaro Spagliani, if I say it correctly, that he was the first one in 1794 that he demonstrated the ability of bats to navigate through dark through an inaudible sound. It was ultrasound. The first mathematical description of sound waves was done by Lord Rayleigh, and this was the tool that we had in the scientists had in order to calculate and grasp the idea of sound. And then the breakthrough for the evolution of ultrasound was the discovery of the piezoelectric effect by Pierre Curie in 1880, because this effect is used in both generation and reception of ultrasound. Now, as many technologies, it started from military use. So after the Titanic was sunk in 1914, the first sonar navigation system for submarines was developed in order to find icebergs before hitting them. Then we have in 1924 the radio detection and aging system, the well-known radar system. The principles of radar system is the exact same principle as the medical ultrasound works, as we are going to see. And then in the 30s, we had the use of ultrasound in metal flow detectors in order to check the integrity of enamel plates in battle tanks. Now, the way that this worked is the same way that medical ultrasound works. They sent it an ultrasound wave. If a crack was inside the metal plate, then an echo was backscattered to the transducer, and we captured it and print it, and then the rest of the wave was traveling to the back of the plate and backscattered again into the transducer, and we get also the second echo. By the time it took to travel through to the crack and back, or to the end and back, we can calculate the depth that the echo is coming from. This is the principle that ultrasound imaging works. Now, the first use for ultrasound in medicine was not done for diagnosis, but was done for therapy. Russell Myers, he was performing craniotomies and using ultrasound to destroy basal ganglia for Parkinson patients. Then it was extensively used in physical and rehabilitation medicine. It is still used in physiotherapy. And in the 40s, the first claims of the effectiveness of ultrasound as a curing modality was made. In the same year, in the 1940s, it was the first paper was presented, scientific paper, that explored the possibility of using ultrasound as diagnostic tool now, and not a therapy tool. In 1946, Daszak was the first physician that employed ultrasound in diagnosis, and he called his technique hyperphonography. Let me minimize that, sorry. You can see here the image of Daszak and his first assembly of ultrasound ever created, diagnostic ultrasound ever created. Then in 1963, we have the first 2D image, the B mode, the image that we all know as ultrasound image right now. And again in 1963, we have the first medical imaging ultrasound device. They called it the sonograph. It was built at Kevin and Hankles at Hingleton in Glasgow. Here is the very first medical ultrasound machine. This picture is from 1664, to be fair. Now, in 1974, it was the first time that a double pulsed Doppler scanner was created that gave the possibility to see and to image blood flow. Now, since then, medical ultrasound have done a great journey. So right now we have real-time high-resolution images of anatomy and blood flow. As you can see here, we have 3D imaging or 4D imaging, as they say, real-time 3D imaging. We can use ultrasound contrast agents. 27% of all medical imaging at least is done by ultrasound because they are economical. They are extremely portable. Right now, it is just a handheld probe with a USB-C that you just plug it in your mobile, let's say, and you have a small ultrasound scanner in your tablet. You have real-time imaging. It's completely safe for the patient. We have no ionizing radiation. We are using low MI of ultrasound waves, so we have no health risk at all. And we can integrate anatomical data with blood velocity in real time. Now, in order to understand the principles, we have to see some basic facts about the sound waves. First of all, you all know that, so I will go very fast. We have the wavelength, is the horizontal length of one cycle of wave. We have the period and the amplitude. What is very important is how all these are connected. We have this equation that says that the speed of sound equals wavelength multiplied by frequency of the wave. So just keep this in mind because it is very important. Now, the speed of sound, as you all know, assume it's independent of the parameters of the sound wave. So even if we're talking about a loud sound, if we are talking of a not so loud sound or a high frequency or low frequency sound, the speed that it travels is exactly the same. The speed has to do with the medium and the characteristics of the medium. Now, since inside the body, as you see here, most of the tissues, the sound is traveling with the same speed, we can say that we have a constant speed of sound inside the body. And based on this equation, we can say that if we increase the frequency, then we have smaller wavelength. This is very important and keep it in mind for the next of the talk. So when we increase the frequency of the sound wave, we have smaller wavelength. So we have the wave traveling inside the body, and at some point, as we said, just like the radar, it hits something. What is that it hits? It means that it passes from one tissue to another tissue. We have a tissue interface. So when we have a tissue interface, then we have a reflection. The reflection has to do with the difference on the acoustic impedances of the two tissues. If we are saying, let's say, about fat and air interface, then we have very, very big difference on the acoustic impedance. So 99% of the wave will be reflected back. So what we can say is that air distributes the transmission of ultrasound waves because only 1% will travel inside the air. And this is the case of the lungs imaging. In the case of the lungs, 65% of the wave's energy will be reflected back, and it is almost impossible to visualize inside the lung. Now, again, even in the case of muscle and bone interface, we have 48% of the wave energy reflected back, and this is a reason that we have difficulty to scan behind the ribs, let's say, the heart behind the ribs. Medical ultrasound, therefore, is limited in soft tissue imaging only, with reflection coefficients of around 10%. The other important physical parameter that we have to know is attenuation. What is attenuation? Is the energy loss of ultrasound when it propagates through the tissue. It has to do with the characteristic of the tissue, and it increases with the frequency. Again, higher frequency means higher attenuation, and as it's very logical, with depth. As we travel, energy is lost, so as we go deeper into the body, we have higher attenuation, higher loss of energy. So here you can see attenuation in different tissues of the body. You can see that attenuation is relatively low for kidney, spleen, fat, blood, etc. But in the case of bone, it is 20 times higher than the rest of the tissues. This means that even if some part of the beam enters the interface of muscle and bone, let's say inside the bone, it will be heavily attenuated. This means that the imaging of the inner structure of the bones is practically impossible due to this high attenuation. You have to be careful here, the inner structure of the bone, because the surface of the bone, we can see them. Here we have an X-ray image, here we have a reconstructive 3D image, and here we have the exact same area scanned with an ultrasound. You can see we see the muscle, we see the soft tissue, and here we see the surface of the bone. We can detect the fracture with the ultrasound, but we cannot see anything inside because most of the sound has been backscattered, 50% as we saw. That's why we have a very white pixels here. And then the wave that was able to get inside the bone, it was heavily attenuated, so no ultrasound wave was able to travel down here. So we have no signal, and that's why it is black. We see nothing. Now, how the ultrasound waves are generated? As we said, we are generating using the piezoelectric effect. What is piezoelectric effect? We use piezoelectric crystals, which are crystals that when you apply voltage into them, a voltage with particular frequency and amplitude, they start oscillate dependently on the voltage that you applied, same frequency, same amplitude, etc. And the very important thing is that they do also the inverse thing. If an ultrasound wave vibrates the crystal, voltage appears at the edge. So we can detect the voltage and thus detect the ultrasound wave. Medical ultrasound systems operate in the range of 1 to 30 megahertz, as you correctly answered, most of you. And I remind you that the audible range is 20 hertz to 20 kilohertz. This means that is outside of our receiver ability. Now, we have the ultrasound probes. These are the things that you see the doctor placing on the skin of the patient in order to create the ultrasound wave inside the body. So the probe is made of a series of piezoelectric crystals, one next to the other. We have a backing layer, we have acoustic lens, matching layer, and if you remember, we always use a gel. This gel is used in order to have same acoustic impedance between the probe and the skin, and to avoid having any air between the skin and the probe, because if we have air, as we said, all the energy, the ultrasound wave will be backscattered back to us. So we use the gel to avoid having air between the skin and our probe. We have different types of transducers or probes. We have single frequency transducer, broadband, or multi-frequency transducers, in which you can choose which frequency you want. And how imaging is done, exactly as radar, we have a sound wave propagating an obstacle. So we have echoes coming back, as you can see here. Let's say that we have 4 different interfaces, echo from the first interface, we get the echo, we print it, and we color the pixels. Then the second, the wave continues to travel, second echo coming back, we print it, then the third echo and the fourth echo from the different depths. We have 3 main display modes. We have A mode, which was the first mode that was ever created, the amplitude mode, the M mode, it was an evolution of A mode, and the B mode, which is the image that you all have in your mind about ultrasound imaging. Let's see them very quickly. The A mode is the amplitude mode. What we done is that they were able to produce images as in a one-dimensional image that only depth data could be measured. We are using sound waves was sent in only one direction, let's say in these directions, in an A line, as we say. And the backscattered echo was captured, the A line was captured and presented in XY axis, where X is the depth and Y is the amplitude. So the wave is traveling, first echo from the retina coming here, we plot it, Y is the amplitude, then the starting of the lens, the end of the lens, and the back of the eye. The amplitude is then, in the modern systems, translated into pixel value. Higher amplitude, whiter, lower amplitude, grayer, less white. Then we have the M mode. What we do in M mode, what we do is that we are sending A lines in the exact same direction, only in this direction, let's say. And we are printing every line one next to the other. So we end up with a graph like that. Here we have a line and here we have time. So what we see here is not a structural image, but we see here the chambers of the heart. We see the upper part of this chamber, how it moves through time. It goes up, down, up, down, up, down. So this is imaging of the motion, but it's not structural imaging, okay? Then we have the B mode, what we all know as ultrasound image. It was a breakthrough in ultrasound imaging. B comes from brightness. And what we do here, exactly as the radar, we scan an area. So we are sending A lines and we are steering them in a whole area. We scan them and we print one next to the other, resulting in our final image. We have many different arrays to do that. The most important categories are linear and convex array probes, in which we have the elements, piezoelectric crystals, one next to the other. And what we do is that we scan by exciting next element of the aperture and resting the last one. And we do this sequentially in order to scan the whole region underneath. As you can see, the imaging area is the same as the size of the array, the width, as you can understand. Then, in order to increase a bit the imaging area, they also created convex array imaging. So you have a smaller footprint, but a bigger imaging area. But still, this is very big. We are talking about 10 centimeters. So if you place it into the ribs, you wouldn't be able to see the heart, let's say, behind the ribs. This is when phased array probes came to solve the problem. It's again arrays with piezoelectric crystals, one next to the other, but much smaller and much closer one to the other. And we apply beam forming. What does that mean? We apply delay on the pattern that we excite its crystal, and we are able now to steer and focus our beam. With that, we have a very small footprint and a very, very big imaging area. And this is used mainly cardiology because we have a very small acoustic window in order to see the heart. Here you can see the difference between the two types of arrays. A linear array, you can see just under the array, the probe, and here a phased array probe, where you can see that in a very, very small footprint, because we scan, we steer and scan, we can see a much, much higher area. How we do that? We do that with beam forming. What does that mean? We apply delays on when we excite its piezoelectric crystal. And as you can understand better here, we can focus, let's say, in the central line, the acoustic beam, or we can steer it or focus and steer it at the same time. So by applying delays on the time that we excite each piezoelectric crystal in the probe, we are able to steer and focus our beam. And then, thus, we are able to scan a whole area. Now let's talk about the resolution. So every imaging system has a resolution. Spatial resolution, as you know, is the ability of a system to distinguish between closely spaced scatterers, let's say. So we have three axes. We have the lateral axis. This is the probe. If we place it like that into the body, let's say, this is the lateral, this is the elevation, and this is the axial, the depth. Let's start with the axial. The resolution of the axial is limited to half the wavelength. Why is that? Because if we have two scatterers, as you can see here, if their distance is higher than half the wavelength, I will have two discrete echoes coming back. So I will be able to print two different lines. So I will see two different structures. But if they were closer than half the wavelength, then this echo would step on the first one, and I would receive one echo back. So I wouldn't be able to understand that I have two different structures in here. What I can do, as we said before, we can use higher frequency, because higher frequency means lower wavelength. So higher frequency, lower wavelength, so it means short acoustic pulses, higher axial resolution, but higher frequency has also the toll of lower penetration depth, because we increase attenuation, as we said. So we have shorter waves, we have better axial resolution, but we cannot see very deep. Then let's go to the lateral. This is the lateral resolution. The lateral resolution has to do with the aperture size, which means the number of elements that we are using. Higher aperture size means that we can create a more focused beam, so higher resolution, while narrow aperture means that we have a less focused beam. Again, here, it is too complex to explain it now in this time that we have. Higher frequency also creates better focused beams. So again, if we use higher frequency, we have higher lateral resolution, but again, we have the penalty of lower penetration depth due to attenuation. And at the end, we have the elevation resolution. The elevation resolution is the resolution in this direction. Now, as if you remember, we have array. In the array, we have elements only, piezoelectric crystals, one next to the other. So in the elevation direction, we have only one crystal. So we cannot have any beam forming, we cannot have any focusing. So we cannot change the thickness of the slice. This is the elevation direction, the elevation resolution, the thickness of the slice, But all this changed with the 2D probes. Now we don't have probes that have elements one next to the other only in one line, but we have an array of probes. This means that now we can have beam forming both in elevation and azimuthal direction. So now we don't scan just a plane, but we scan a whole volume. And this opened the era of 3D imaging in medical ultrasound. You can see 2D image, 3D, 4D as they call it, it is real-time 3D, and reconstruction. You can see it is mainly used in obstetrics, that's why you always see babies. You can see how good results we can have. You can have live images of fetus inside the body, or you can have, let's say here inferior vera cava, in 3D volume, and you can measure very, very well the volumes of the blood, etc. Now, as we said, ultrasound imaging also gives us the great advantage of being able to image the blood flow. How we do that? We do that based on the Doppler effect. The Doppler effect, I meant you, is just the effect that when an echo is coming back from a moving object, it will have a phase shift depending on the direction and the speed of the moving object. So the moving object here is the blood. So we get this shift of the frequency shift, we calculate it, and then we are able to understand the direction and the speed of the blood. You have seen, all of you have seen images like that. We are using red and blue coloring. Don't get confused. Red doesn't mean red that it is artery and blue is vein. It is just a convention that if the blood is moving towards the transducer, we color it red. If it's moving away the transducer, we color it blue. So if I place the transducer here, I have a color Doppler, the blood will be coming back from my veins towards my transducer. So it will be painted red. And if I just do this, the blood will be going away of my transducer and it will be painted blue. Modern systems use other ways to estimate it. Here you can see an example. Here we have B mode, structural image. Then we have the color Doppler. We have blood flow visualized superimposed in the structural image in the B mode. Then we have pulsed Doppler. In this precise region, we can with high precision, measure the exact speed of the blood in centimeters per second, only in this region. And then we have what we say triplex, which is altogether B mode, structural data, color Doppler, and pulsed Doppler at the same time. This is the triplex. Finally, what we have also in ultrasound is that we can also use ultrasound contrast agents. Why we use them? Because we have very weak reflections of ultrasound coming from the blood. It is 60 dB smaller than the tissue. So we use ultrasound, we use microbubbles. It's a small bubbles that contain gas that are about 3 micrometers, which can oscillate and break when insonified. These are filled with air, so we have very good signal coming back, and we are able to even detect blood flow in microcirculation. In other terms, we can replace the gas inside the bubble with drugs, and we can have target drug delivery by that, which means that I inject gas, the microbubbles with a particular drug inside the blood flow. I place the transducer here with high emite ultrasound, and I break all the microbubbles only in this area. The drug goes only here and not in the rest of the body. Here you can also see a video, it doesn't play, sorry, of the resulting image of the microbubbles coming inside the imaging area. You can see how much better we can discriminate all the veins, or a lesion inside the liver. I think this is it. Thank you very much. I'm sorry I was a bit over time. I hope that you understood something.
Evcharisto Poli, Aris, that was an expert and excellent journey through the field of ultrasound from the very beginning to where we are now. Clearly you are a master of the subject, so thank you very much for taking us on that journey. I'm not sure if my fellow panelists have any comments or questions to ask of Aris. I don't see any questions as yet in the Q&A from the audience. Please remember that you always are able to ask questions and post questions there, as well as comments in the chat. So if there are no questions or comments from panelists, thank you once again, Aris. Let me move on to our second speaker. Professor Dan Clark leads the Clinical Engineering Service, which is one of the largest in Europe, at Nottingham University Hospitals, or NHS Trust. He holds an honorary chair in the Faculty of Engineering at the University of Nottingham, and he's co-director and founder member of the Centre for Healthcare Technologies. He also chairs the NHS Trust's Medical Devices Group and sits on a number of trust-wide risk committees. Prior to that, Dan was expert member of the Medical Technology Advisory Committee of the National Institute for Clinical Excellence, many of you know that as NICE, for 10 years until he stepped down in 2019. Dan was awarded by the recently deceased Queen Elizabeth an Order of the British Empire in 2021 for services to clinical engineering, particularly during the COVID-19 pandemic, with his leadership of teams both at the NHS Trust and nationally that responded to the unprecedented and urgent demands for medical equipment. Professor Clark is also Vice President International of the Institute of Physics and Engineering in Medicine in the UK, the fellow member of the GCEA Founders Council, and editor of the Global Clinical Engineering Journal. Dan, it's a pleasure. The floor is yours.
Mladen, thank you so much for those kind words of introductions, and thank you to GCEA for organising this webinar and for entrusting me with this presentation today on the maintenance of ultrasound machines in hospitals. Now, I have to say, I'm particularly nervous right now. I mean, following Aris, who is a renowned authority on ultrasound, would be hard enough. But I should also confess right at the start now that I am not what you might describe as an expert on ultrasound maintenance. I am a clinical engineer of 37 years experience, almost all of which has been in the acute hospital sector. So I do have a level of expertise on medical equipment maintenance in general. I'm currently, as Mladen has just said, head of service for a very large clinical engineering team in a large teaching hospital in the NHS in the UK. We look after something like 75,000 items of medical equipment, including all the therapeutic and diagnostic ultrasound machines. So I guess I should know a little bit about this subject. But it is a tricky subject. So what I thought I'd do today was just touch on a few basics of healthcare technology management in general. Then I'll discuss why I think ultrasound machines present certain additional challenges. And for the sake of this presentation, I'm really focusing on diagnostic imaging, but the principles are the same for therapeutic devices. Then I'll describe our approach here in Nottingham. I'm not claiming it's the best approach, but we've been struggling it for a while, and I think we've probably got it about right. And then I'll finish up by looking at some of the lessons that we've learned in establishing the way that we manage ultrasound in our hospital. Next slide, please, Calibration. So just to give you a flavour of what we're about here in Nottingham, we are a major teaching hospital. We've got 3 main hospital sites, including this one on screen now, plus a couple of satellite units, and we also support equipment in the community. I think we've got in total something like 60 operating theatres, over 200 wards, 2,000 bedded hospitals in total, and we provide a whole range of clinical services, both local services and specialist regional services. It's a very large clinical engineering team to support all of that. I think we've got about 120 staff at the moment, about half of whom are employed in medical equipment servicing, including, of course, looking after ultrasound machines in our hospitals. Next slide, please. So if we just have a quick look then at healthcare technology management in general, and healthcare technology management is about much more than just equipment maintenance, of course. It's about how we manage the equipment throughout its entire life. Indeed, you might say the process starts before the equipment is even born, and progresses right the way through till after it's been retired and decommissioned. This slide might be a little bit too detailed for you to read all the writing, but maybe we can share the slides later. But the healthcare technology cycle, it describes our depiction of the healthcare technology cycle, outlining all the major processes along the way. So any item of equipment, ultrasound machines or anything else, will flow around this cycle during its lifetime. And the thing about a cycle is you can start anywhere and go around it, but for convenience, we'll start at the top of this cycle with a sort of purpley coloured arrow. This is the planning process. This is where we decide what our patient needs are, what technology might be able to provide for those patient needs, and how we can go about meeting that need. Then we move on to the, once we've decided that, to evaluating available technologies and which technologies that we select, which would be most appropriate for our hospital, for our healthcare system. Once we've done that, we need to procure that equipment, during which we need to make sure that that equipment is approved as being suitable to meet our needs. And then we buy it, it gets delivered, and once it's delivered, we need to commission it. This is a process through which we make sure both the equipment is made ready, so it's tested, it's checked, it's inventoried, but also the organization is made ready. So we train our users, our clinical users, and we make sure any configurations are put in place. Having done that, we actually deploy the equipment into clinical use, and hopefully this part of the cycle might last many years, during which time the equipment will need quite a lot of technical and non-technical support to keep it effective and efficient in use. At some point thereafter, it needs to be retired from service and decommissioned, perhaps when it becomes obsolete, becomes beyond economic management, or perhaps simply when we no longer need it, when we no longer need that type of equipment in our hospital. At which point it needs replacing. And so the cycle starts again as we make plans to replace that equipment. So next slide, please now, Calibration. So that's a large process. I'm probably telling you things you already know, but for today, I'm just going to focus on 3 key steps within that. That's the approval stage, the commissioning stage, and then the equipment maintenance stage, and which is actually a lot more than just the technical maintenance of the device. So we might better refer to that as the operational management phase. So I'll come on to the detail of each of those steps in just a minute. But before I do that, I want to look at why we think managing ultrasound machines in hospitals is particularly challenging. Next slide, please. So it is a challenging technology to look after in a hospital environment. And I think there are 4 broad reasons that make managing this type of medical equipment so tricky for us. Firstly, ultrasound is used in very many clinical applications, and in each one it's used slightly differently. From obstetrics, which is perhaps the most common, through to vascular, to renal, to bladder scanning. It's used in urology. It's even used in our emergency department to identify foreign bodies when x-rays won't help. Our clinical colleagues, they want different things from their ultrasound machines. Different precision, different image quality, different resolutions, but they also want the same things. They want rapid response times. They want the latest technology. They want maximum clinical uptime. And of course, they want value for money. What the clinician needs, what the clinician wants, tends to win out. And so the clinicians will have a whole range of priorities about what they want. And what we find is within a hospital environment, there's no single clinical contact to help us coordinate all our activities in these different areas. they don't really have anything in common with each other. Obstetrics and vascular, for example, they don't have anything in common, and this can lead to different expectations out of the service that we provide, different priorities, all of which makes it a challenging area to try and coordinate the service that we provide. Next slide, please, Calibration. So secondly then, there are lots of different makes and models of ultrasound machines in use in our hospitals. We all know the advantages of standardizing on medical equipment, but with ultrasound, we find that very difficult to do. At last count in Nottingham, I think we had 1,800, very nearly, ultrasound machines, but there were 31 different models, and I think we have 6 different manufacturers currently. So we know the advantages of standardization. It's certainly very helpful if we've got a single or a small number of manufacturers. It reduces the amount of stock of spares we need to keep. It's easier to keep our technical staff trained if we've only got one manufacturer, and it's easier to get responses out of that manufacturer if we've only got one. But of course, because we've got this challenge of ultrasound being used in so many different clinical applications, it naturally leads to different clinical preferences. For example, Sonosite might be the clinical preferred choice for bladder scanning, whereas Philips might be the choice used in obstetrics. And then again, Toshiba might be the choice we would use in cardiac, whereas GE might be the one we go for in vascular, and so on. Of course, clinical preference is important, and we need to support our clinicians in making the correct choice for their clinical application. But as a result, that leaves us as a support service having to manage a wide range of technology from a wide range of suppliers. Next slide, please. And then, of course, ultrasound machines need probes. It's perhaps the most challenging aspect of managing ultrasound machines is managing the probes. Now, a lot of ultrasound machines use multiple probes, not just the one probe, and we all know what it's like trying to manage equipment that has accessories, and particularly that has multiple accessories in our hospitals. Accessories get moved, they disappear off into different parts of the hospital. Some machines use multiple accessories, they all get mixed up. And when we have ultrasound machines, we have the added problem that we need to worry about the image quality of the probes, even when they're moving around. When we turn up to service equipment, they might not have all the probes with them. And the next time we come back, they may have a different set of probes. It just adds to the level of complication of trying to provide a support service for ultrasound machines in our hospitals. Next slide, please. And the final challenge is that about the number of skills that we need to support these machines. In order to support ultrasound machines effectively in our hospitals, we need to utilize a diverse range of skills. Generally, those skills are not found in a single staff group. So we end up using different teams to look after our various ultrasound machines. That includes the in-house clinical engineers. It can include external servicing agents. It might include imaging specialists, for example, from medical physics. It's going to include our sterile service team for cleaning and reprocessing. Not to mention, these devices are often networked and use patient identifiable information in them. So we need to involve our IT department and our information governance teams. So all in all, there's a complex range and indeed complicated set of logistics to try and coordinate. So if those are the challenges that we face, how have we here in Nottingham tried to manage all of that? Well, once upon a time, we used to try and do everything ourselves within the clinical engineering service. But we realized after a while that we couldn't provide a high enough quality of service if we were trying to do it all on our own. And so we've now deployed a multi-team, multi-stakeholder approach. Next slide, please. Okay, so you'll remember at the start I said we were going to focus on just 3 aspects of the equipment lifecycle. And those 3 aspects start with approvals. So the approval phase really should happen before you buy anything, before you make any financial or contractual commitments. Here in Nottingham, in order to do our approvals, we use a pre-acquisition questionnaire, or PAQ. And we send that out to the supplier, to the manufacturer, to gather essential information on how to manage, how to support, how to look after the equipment, any equipment, not just ultrasound machine, any equipment. The PAQ was actually developed in Nottingham, but has since been adopted by the UK Department for Health. The PAQ is a 5-page document which we require our manufacturers and suppliers to submit information about their product. This information covers everything from regulatory compliance to product support to technical support to implementation guides to information about safety and cleaning. And when we've gathered all the information via that PAQ, we then undertake a series of internal stakeholder reviews. We do that with the clinical teams, with the technical teams, with the imaging physics teams, and with our sterile services, as well as our data governance and IT groups. And at that stage, we review every aspect of the ultrasound machine, its accessories, including the probes, and we understand from that how we're going to manage it throughout its whole life to make sure it's compliant with our expectations and our rules and regulations, and to get the best value for our clinicians. It's quite a heavy step. It's quite difficult to get this step right, but it's an essential first step. Everything else throughout managing the equipment throughout its lifetime will be determined by how thoroughly we do this first approval stage. Next slide, please. So having approved the device, we can go out and buy it. And then when it gets delivered, we take it into the commissioning stage. Now, the commissioning is a complex process, which takes us from the delivery of a new device in its cardboard box arriving in our hospital. From there, we need to ensure that everything that we've ordered is actually delivered as expected. We need to check the functioning and safety of the equipment is within our expected tolerances. It needs to get inventoried onto our equipment management database. We need to set up planned maintenance regimes for future work, for future checks. We need to make sure our clinical teams are ready to receive it. Have they received training? Are they competent to use it? We need to establish any set of specific local configurations and get them set on the machines. And then finally, we can deploy the device into clinical practice. Now, if you've done your approvals right, most of this is relatively standard stuff, and our in-house clinical engineering team perform most of these tasks. However, a really key step when it comes to ultrasound devices and what makes them different from say, an infusion device or an electrosurgical unit, is that we also need to check the image quality and functionality. And in Nottingham, we do that by relying on our medical physics colleagues who do the image quality checks using phantoms. It's an interesting thing to note that generally, when we're commissioning equipment, and we commission something like 5,000 items of equipment every year, we generally find over all that equipment that we get something like 3% rejection rate, what our team refer to as out-of-box failures. So this means that some aspect of that commissioning process, some aspect of those commissioning checks have not been passed. And at that stage, we'd have to go back to the supplier, back to the manufacturer, either to get a replacement or some other way correct that failing. So that's a 3% on general medical equipment. But it's notable that for ultrasound devices, ultrasound probes, that rejection ratio is very much higher. In fact, it's very much closer to 10%. So nearly 1 in 10 of all newly delivered ultrasound probes fail some aspect of those performance checks at commissioning, and we need to return them or get the manufacturer in to support us and get that put right. So it just underlines the importance of getting those commissioning checks done. Next slide, please, Kelly. So, okay, now we've approved the device. It's been ordered, it's been delivered, it's been commissioned, we've deployed it. It's now out there in clinical land being used, and hopefully it'll be used successfully for a long time. And we now need to make sure that we can manage that equipment and support that equipment and its probes and their accessories throughout its lifetime with us in the hospital. Now, although this is a multi-stakeholder process, a multi-stakeholder event, that whole process is managed and owned by our in-house clinical engineering team. So once deployed, the planned maintenance regimes, the repairs, and any other aspect of looking after the equipment is managed through the equipment, the clinical engineering team. And even though we use external agents and other teams to deliver certain aspects of the technical service, usually under a contract. So scheduling of that contract, scheduling of planned work will always be done through our in-house clinical engineering team and through our inventory management system. Whenever we're using external agents, the contract needs to be regularly reviewed to make sure that the external agent are indeed doing what we've asked them to do. And this will include monthly performance data. It'll include activity reports, incident management, and systems in place to escalate and make sure we put things right if things are going wrong. And all of this should have been sorted out and agreed at the approval stage. Again, underlying why the approval stage is so important. Another important consideration when using external agents as part of any maintenance regime, whether it's ultrasound or anything else, is what happens with patient identifiable data. Many devices nowadays will gather data on our patients or be linked to our patient management systems. But this is particularly the case with any imaging system, any imaging device. So it's therefore important to have a process in place to control how we manage patient identifiable data, to make sure it's sanitized or removed before we give control of the ultrasound machine to an external agent. Failure to do so could be a breach of data protection legislation in the UK and certainly lead to fines or even prosecution. We have one example recently, well, not that recently, one example where a manufacturer, who will remain nameless, did indeed take patient identifiable information from our ultrasound machines and use that information to develop and improve their scanning algorithms, which may have been useful for them and may ultimately have improved the equipment, but it was nonetheless a breach of data protection rules and a breach of the commercial code of ethics. And so now we have to be incredibly careful and make sure we have robust systems in place to sanitize the data, control the data, and get certificates to confirm this. So clearly, technical quality of service is really important, but we need to recognize and understand whenever we're using external agents to do servicing for us, that their standards and expectations might not be the same as our own. So again, it's important to be clear about all this, these expectations at the very outset, at the approval stage, and be able to monitor against these expectations during the lifetime of the contract and the support. And I mean, an example of that is our in-house team will always work to electrical safety standard 60601, whereas most external agents use the slightly less robust 62353 electrical safety standard. And similarly, our in-house teams have very high standards when it comes to checking for damage and wear and tear on devices, cracked cases, scuff marks, signs of fluid ingress. They're likely to be much more vigilant on that than an external service agents tend to be. Gets further complicated if your external servicing agent is not the original manufacturer. And today's not the day to talk about the pros and cons of using independent or multi-vendor services. But you do have to be particularly vigilant if you have a non-OEM service supplier to make sure that their technical staff are appropriately trained and competent to do the work that you've asked them to do, and to make sure they have access to the right parts and the right support from the manufacturer. Of course, all of this relates to the technical servicing aspect of managing the ultrasound machines. But one of the other challenges that we have, of course, with ultrasound is we also need to provide assurances of the image quality. So again, it's important to be able to have access to independent imaging experts or have a good relationship with a medical physics department or similar who can respond quickly and provide image quality assurance checks post-commissioning and post-servicing. Finally, it's worth saying a thing about decontamination. We know, of course, that decontamination can damage probes by the nature of the cleaning or the chemicals used. So again, it's important to establish the cleaning regimes at the outset, at the approval stage, and make sure these are well understood and assessed in advance. Next slide, please, Calibration. So that's our approach here in Nottingham. We've moved from a position where we tried to manage all of this in-house with a single clinical engineering team to a system that we now have where we use multiple stakeholders to do various aspects of our management and support of our ultrasound machines. We're not claiming it to be a perfect system, far from it, but we've been wrestling with these challenges for quite a while now, and we think we broadly got this about right. So some of the key lessons that we've learned along the way, Firstly, manage people's expectations. One of the challenges of this type of activity is that different stakeholders will have different expectations out of your service support. Interventional cardiologists are going to want very, very high image quality, a bladder scanner nurse and much less. In-house technical teams tend to work to very high technical service qualities. External teams might be more focused on the speed of service rather than the quality of service. So it's important to be clear at the outset with everybody what everybody needs from the service, and equally clear what the limitations might exist and what compromises we might have to employ. It goes without saying, almost everything we do as clinical engineers, communications is vitally important. So make sure all your stakeholders are involved and on board at the very start of the process, at the approval stage. And remember that it's hard to over-communicate. Much better to say something twice than have some of your stakeholders unaware of what's going on. Understand and possibly accept that there are limitations to the quality of the service that you can provide through this system. There will be differences in qualities when you've got multiple stakeholders involved. So just make sure you understand that. And if you're going to accept a lower level of service, understand the benefits that that might bring, as well as the limitations. As I said, we here in Nottingham, the clinical engineering team, manage the whole process, from initial planning to approvals to commissioning and to the in-service support. We do utilize other resources, so medical physics, external servicing agents, and the internal sterile services teams, but we nonetheless provide that end-to-end service on behalf of our clinical teams. But don't underestimate the length of time it takes to actually manage that whole service and keep the whole thing working as a single process. One of the key frustrations that we've had in the past is the availability of probes. If a probe breaks or we need to bring in a new probe, it will need to go through image quality control before we can issue it to clinical service. And this takes time. But the clinical teams are often really, really busy and they haven't got that time to wait. So that leads to frustrations. So one of the things that we did and lessons that we've learned is that we've overcosted so that we can provide additional probes in certain clinical areas to create, if you like, a virtual library of probes which are already tested, they're clean and ready to go. In this way, as soon as there's a problem with the probe, a break or damaged probe, we can immediately swap it out for a new one out of our equipment library stock, while we then take the time to service, repair and retest the damaged probe. Finally, money. Money is always a big issue. So we need to be clear with a service like this about the total cost of running the service. Finance directors often just see the cost of the external contracts that you put in place, but it's important to recognize all these other costs too: the medical physics team, the clinical engineering team, the sterile services, and others. So cost it all, otherwise your finance director might think that the external agents appear artificially cheap. Next slide, please, Callie. And that's me. Thank you ever so much for your patience in listening to all that. Like I say, we're not claiming it's necessarily a perfect system, but we think we've addressed most of the challenges that there are with managing ultrasound machines in a busy acute setting. And we think we've covered most of those challenges off with the multi-stakeholder approach that we've got. So thank you very much for listening.
Thank you very much, Dan. Another excellent presentation, a journey through a very complex space, and you touched on so many important points from your vast experience and the experience of your team. There are some questions that have come in. Unfortunately, Dan, they're mostly in your direction, so I'll keep them fairly short, and perhaps you could respond as appropriate. So there's a question from Anusha. I guess this is a practical question. I've heard that ultrasound machines should not be connected to the plug point where other supply sockets are connected. I guess sharing multiple equipment, sharing one plug point. This may cause noise in image quality due to leakage current. Is this something that you've encountered at all? Or perhaps fellow panelists?
I'm not completely sure I've got a definitive answer to that one. So, but we would never, unless we we're in an emergency situation, ever use multiple outlets for different clinical electrical clinical equipment. I'm not sure if you mean when you say a supply socket. We don't use independent supply for our ultrasound machines, and I'm not aware that it causes image quality difference. Of course, if you put any multiple equipment in a multiple outlet socket, then you do increase return currents. You do return earth currents. You do also reduce the security of your supply, and you can increase surface leak currents. But unless Aris has an answer in terms of the image quality, I'm not aware of a problem with image quality.
Thank you, Dan. Aris, would you have a comment or not?
I cannot answer with certainty, but it seems difficult to me to have any effect in the imaging. Okay, maybe if you have noise in the electronic part, then the ultrasound part, of course, the sound part will not be affected. Now the noise, the electronic noise in the rest of the system, okay, but I think it's a bit difficult to happen, I would say, but I cannot say with certainty.
Thank you. Another question's coming, Dan. Your thoughts on handheld ultrasound becoming more popular and available due to lower cost? For example, managed particularly with regards to data security, and then tablets and phones. So it's kind of a loaded question. Perhaps just your thoughts on handheld ultrasound. And I mean, from our own experience, these were promoted and used, in fact, as part of the COVID pandemic response. But your thoughts on handheld ultrasound? Okay,
so in terms of functionality and image quality, I'm afraid I'm not expert enough to answer that. Like you, Mladen, we've seen an acceleration of handheld devices, mobile devices used in the community, including ultrasound machines which work on mobile phones and tablets. They bring huge benefits in terms of accessibility to patients. They bring huge benefits in terms of low resources. They bring huge benefits in terms of a flexible clinical service. There may be limitations, and I'm not competent enough, so I'm not going to answer this bit in terms of the functionality, the precision. But I don't believe that's the case, because and Aris, I hope, might have more on this. The image resolution comes from the probe, not from the tablet or the phone. But the issue, the last line of that question about data security, that is indeed a loaded question. It's a phenomenal area of concern in the UK, in the NHS, about patient identifiable data being lost, being corrupted, partly for security, but partly for misuse. We have all sorts of issues with that, not just in ultrasound, but in a whole pile of devices which we're now using in domestic environments or in community care environments. We try very hard to use modular platform systems. So the tablet would connect to another software system, and we can put firewalls and data security on that. What we don't like in my hospital setup and my community setup is standalone tablets and standalone phones using apps. So we discourage that. But having said that, in some settings, the advantages of having a device that you can quite literally put in your pocket and drive around to the patient outweighs the risks of data security. But not in the NHS. We're particularly risk averse on that data aspect.
Thanks, Dan. And then if I may address the final question again in your direction. Question about usability. So your pre-acquisition questionnaire does not seem to address usability. Do you conduct usability studies, or in your opinion, does it come down to, say, just simple user preference, which may not be able to definitively define in a questionnaire?
So I agree with the questioner. Our PAQ does not does not evaluate medical device technology. The PAQ is about understanding how we will manage that technology moving forward. So it doesn't evaluate it at all. We would separately, if we went back to that first or second slide of mine with the life cycle diagram, one of those arrows there is around evaluation. So depending on the product that we were looking at, we would most certainly instigate evaluations. They would be, depending on the technology, they might be benchtop, they might be evaluated via literature search, they might be evaluated. We have a simulation center where we do evaluations of medical device and user needs and user assessments, and we do short evaluations in genuine real life clinical settings. That's a separate process that doesn't form part of our approvals. Having done that and chosen it, we then use the PAQ to decide what information do we need to manage it safely through its time with us. So they're kind of separate processes for us.
Thank you, Dan. Thank you for those responses. There are more questions that have come in, but unfortunately we do need to close. We will capture the questions that have been posed, and we will endeavor to present them to either Dan or to Aris, and then respond to you offline. But for now, it remains for me to thank both presenters. Dan has been awarded the OB, but I'm sure the audience this evening will agree that both presenters deserve the order of the MEP of Most Excellent Presenter. I was glued to both presentations, and I'm sure many of those watching were, so thank you so much. Just a reminder that the webinars are available in a repository on the GCEA website. There is a webinar repository, so if you'd like to revisit this or any other webinar, please feel free to do so. Also a reminder that this is the first of a series of 3 webinars on medical imaging technologies. In October, specifically October the 12th, we will be looking at magnetic resonance imaging. And in November, on a date yet to be confirmed, we will be looking at computed tomography. But for now, I'm not, unless Kaliroy has got any closing remarks.
Thank you all for a wonderful webinar. Thank you. Thank you.
Yes,
looking forward to the next.
I would once again want to thank Aris and Dan for excellent presentations, and thank you all for attending. And I look forward, like you all do, I'm sure, to the next webinar. Thank you so much, and good night.
Thank you.